We are starting with Rao Bhim 7.2. Definition 7.2.1, we have a vector space over the field is either R or C. An inner product on V is defined as a function from V cross V to F, which combines two vectors into a scalar, which we denote by this angle bracket notation in the book, such that it satisfies these three conditions. For all xy, we have this commutativity with complex conjugate relation. This is complex conjugation. Some kind of a distributivity for all alpha 1, alpha 2 scalars and vectors x1, x2, y. We have this kind of distributivity. Observe that it is only given for the first component of the inner product. 3. For all x in V, we have xx greater than equal to 0, and it is equal to 0 implies that x must be equal to the 0 vector. A vector space together with an inner product is called an inner product space. We have already seen this definition in the last video. In that video, however, we had not just implies but if and only if in this place. It really does not matter because by property 2 we must have inner product of 0 with 0 is same as inner product of minus 0 with 0 because minus 0 is same as 0. By property 2 the minus comes out, so it is minus of 0 with 0. As a result, we have inner product of 0 with 0 is equal to its own negative, and that forces it to be equal to 0. In this definition, notice that we have got f is either R or C. Now, if it is R, then in property 1, this complex conjugation will have no effect because for every real number, its complex conjugate is itself. Here is the most popular example, example 7.2.2. The vector space is Rn over R. If we take any two vectors, x1 to xn and y1 to yn, then their inner product is defined as summation xi yi. Now, if I consider the vectors as column vectors as here, in that case I can write it as x transpose y or equivalently as y transpose x. Next we look at its complex version. Here the vector space is C to the power n, and again I take two vectors x and y where all these xi's and yi's are complex numbers. Then the corresponding inner product will be summation xi yi bar, that is complex conjugate. Notice that this bar sits over y, the second argument. If you put the bar over x, then it will not satisfy all the properties of an inner product. And if we want to write it in terms of a vector notation, then we can write it in this way. It is y star x, where y star is same as y transpose, and then you take a complex conjugate of that. So this is called conjugate transpose. So this is the definition. And again, if you put the star on top of x, in that case, it will not be a inner product. This next example is more non-trivial. Now, checking the three properties of inner product is quite straightforward. First of all, if x and y are swapped, then this remains the same because you can see then x1, y1 remains the same, x2, y2 remains the same, and x1, y2 becomes x2, y1, and both of them occur with the same coefficient, so that also remains the same. Now, property 2 is also easy to check. Now, for the third property, we have to note that inner product of x with x is, after some steps, equal to this thing, which is sum of two squares. Now, how did I get this? This is just by completing squares. Now, clearly, this is always greater than or equal to 0. And also, if it is equal to 0, then both the square terms must vanish because we are working with real numbers. which means I must have x2 equal to 0 and x1 minus x2 by 2 is 0. Since x2 is already 0, that forces x1 and x2 both to be equal to 0. In other words, x has to be the 0 vector. The next example is more general. Here we are working over the complex field, the vector space is Cn, and we are given this particular form where B is a non-singular matrix. Remember, the star denotes conjugate transpose. Now we are going to show that this is indeed an inner product, that is, we shall check the three properties one by one. The first property wants us to check whether these and these are the same. I have just written this thing using the definition with x and y swap. So x star comes first and y goes to the end, and this complex conjugate over everything. What we do is we bring this complex conjugate inside. Remember, star is conjugate transpose. So when I put the conjugate inside, the conjugate cancels off. I am left with only the transpose. Similarly, b star becomes just b prime. B, so this will become just its complex conjugate b bar, and y will become its complex conjugate y bar. At this point, we are going to employ a trick. Just observe that this quantity is a 1 by 1 thing, that is just a number. As a result, if I take its transpose, it remains the same thing. So I will take transpose of this, which is the following. I will take this y bar and take its transpose to the left. So it is y bar transpose. Then I will take b bar and take its transpose. Then I will take b transpose. Its transpose is just b. Finally, I will take this x transpose and its transpose is just x. Now observe that if I take transpose as well as conjugate, that is what we write the star operation, so it will be just y star. Similarly, this is b star, and this b remains as it is, this x remains as it is, and immediately I recognize this as same as this, that is this. So I have proved that this is indeed equal to that. And that finishes the proof of property 1. Next we shall prove property 2. Here I have to show that this inner product will split up over this part. So alpha 1 times x1y, then alpha 2 times x2y. I have just employed the definition, this definition, and expanded it into this. I observe now that this is just like a matrix, and I am multiplying with this matrix this thing. Now I know matrix multiplication is distributive, so A will multiply this and A will multiply this separately, and alpha 1, alpha 2 being scalars, they will come out of the multiplication. And hence we get this expression. Now I recognize that this is nothing but inner product of x1 with y, this is inner product of x2 with y, hence this is exactly what we wanted. I have split it up into two parts, and that finishes the proof of property 2. In property 3, we have to show that if I take x and x, then this quantity is going to be a non-negative real number. I employ the definition and I get this. Now if I call this fellow the vector z, immediately this becomes the conjugate transpose of z or z star. Now remember, z is a vector of Cn, so it is z1 to zn, where each zi is a complex number. Thus I can write this thing as a row vector times a column vector. I have z1 bar here and z1 here. They get multiplied. Then z2 bar with z2, z3 bar with z3, and all in all I get summation mod zi square, which being sum of certain moduli must be greater than or equal to 0 as required. Now I have to check what happens if this is equal to 0. If this is equal to 0, then I immediately see that all these zi's must be equal to 0. In other words, z must be the zero vector, but I need to show x is the zero vector. But what is z? Z is bx, so I have bx is zero vector, and it is here that I use for the first time the fact that b is non-singular, so x must be b inverse 0, and that is equal to 0. So that finishes proof of property 3. Now what the book does not tell you about this example is that it is the most general example over Cn. That is, if your vector space is c to the power n over c, in that case any inner product must be of this form for some non-singular matrix B. And not only that, if you are working with Rn, then also the same thing holds, except that now you will have transpose and transpose. Of course, then the order doesn't matter. You can even bring X transpose here and Y there. So this will be the most general inner product over Rn. In the last video, we talked about how all these inner products are actually coming from choice of different bases. They are nothing but our familiar dot products with respect to certain specially chosen bases, and this fact actually is closely related with that. But we shall go into these details much later, and for the time being, I will stop here.